Then we use the 5 model, 1 crystal structure and 4 models to conduct virtual screening. Before screening a library, we usually will do a benchmark study, like called retrospective studies, to identify strategy to really get high early enrichment. As I talked previously in the SARS CoV 3CL is very similar to SARS CoV 2 3CL protease. So the biochemical data from historical study on the SARS CoV 2 3CL protease can be used relatively reliably for the retrospective study of SARS CoV 2 3CL protease. Considering the high sequence similarity, and especially for the binding pocket, all the residues are almost the same. So we construct a small benchmark set for the docking study. It includes non-covalent actors, 12 from SARS-CoV-2 studies from Professor Zhang's group, and another 11 is from the SARS-CoV 3CL protease studies with IC50 lower than 100 nanomolar after clustering. Due to the limited data, we only found around 170 experimental inactives from historical data with IC50 lower, greater than 15 micromolar and inhibition rate lower than 20%. The reason we use experimental inactives because we want to mimic the real situation, although the number is relatively small. So we screen this the benchmark set on different protein conformations, and we evaluate the ensemble ranking, which include relative protein flexibility and see how it works. And here's the left for this table, the left column just shows like which crystal structure or which homology model we used. Based on the analysis, we see on top 2%, which is like top 4. The docking score can identify 2 actives, which is half with the top hits. When we look at the top 15, which is like actually top 30 around, the docking score can identify different actives based on which model you used. When we do the ensemble docking or ranking, we see that there's more hits, more actives have been identified. We're also using different scoring functions to post-process the docking, and one is like MMGBSA, which is a force field-based score, and also another is DL score, which is a deep learning score trained on the experimental active inactive data. Overall, we see that ensemble docking based on the docking score gives the best early enrichment. We will use that for prospective screening. Also, another observation is that we see it is relatively difficult to differentiate active from experimental inactive, considering the benchmark studies to differentiate active from putative decoys, because putative decoys usually have a similar physical chemical properties like a molecular weight C-log-P, but have different topology. But for the experimental inactives, usually they have similar topology, even similar physical chemical properties. So it's relatively difficult. But we want to use this benchmark study to really mimic the real situation. And we also observed that the MMGBSA rescoring of the docking study on the crystal structure gives a relative comparable early enrichment, and due to the small benchmark set we are using this strategy as well in the prospective virtual screening. This slide gave a demo how we use the virtual screening to screen a reframe library for the drug repurposing purposes, but the general approach can be applied to other the virtual screening of other libraries. So the reframe library contains around 12K compounds with demonstrated safety in human, including approved drugs and drugs in clinical stage. So we do the ensemble. Here's the workflow of the virtual screening. So we screen the reframe library against each model, and we do the ensemble ranking based on the docking score, and to include the flexibility shown in each model. And we also rescore the screening result against this crystal structure using force field-based rescoring functions. And we finished the first cherry pick and identify 50 hits and ready for the experimental test. And we also use a molecular dynamics-based approach to rescore the top hits to include more protein flexibility. And we will do the second cherry pick and then and the tested experiment. So among the first round pick, that 50 hits, there are compounds which are not included in benchmark. Later show the potency in experiment conducted by other groups, which are published. One is the Navio, the structure is shown here, which is the HIV protease inhibitor, which also demonstrate a cellular potency. Another compound is this one from a reframe library as well. This compound also demonstrates the cellular potency as well, although it's a covalent. It's kind of surprising. The main reason is that the virtual screening is kind of a rough classification model, so it can happen. As the COVID-19 can stay permanently for a very long time, where there are efforts to identify new chemical matters in the long run. Our institute also joined that effort. As I mentioned before, that there are historic data on the SARS or MERS 3CR protease there, and also also studies on the other cysteine protease. What we learned from these data is that there are peptidomimetics compounds, and also there are small molecules as well. They're covalent inhibitors, and they're also non-covalent inhibitors. Normally, it's relatively challenging to get potent non-covalent inhibitors. So these data can help us to really to design what type of inhibitors in the drug discovery. Here on the left figure, just to show a binding pocket with peptidomimetics covalent compounds bound. This is published on Science this year, and this compound has a relatively good PK. To identify new chemical matters for the hit discovery stage, as I mentioned before, that we can use virtual screening to screen a large diverse library with normal chemotypes. We also can reevaluate the hit from historical data, how this hit works on the SARS CoV-2 3CR protease. And once we have a hit on the hit to lead and lead optimization stage, if we want to design covalent inhibitors, you probably need to identify selective warheads. QM-based models can help predict the reactivity and somehow tune the warhead reactivity to potentially help the selectivity study. And also, we need to improve potency. Usually, we can, enumerate the library for the subpocket. For the protease, there's different subpockets here. For example, here, this is S1 binding pocket, S2, S3 is solvent exposed, this is S4. There are also S1 prime pocket here. So we also can do rational design based on structures and enumerate compounds or design compounds by covalent docking, or even further using MD-based approach to estimate binding affinity, etc. As we want to make a drug, we need to improve the drug-like properties, like we can use the admin tox predictions to help Medichem to evaluate the drug-like properties. In the end, thank you for listening. I hope you find this class interesting and have a taste of how a computational approach applied and assist to the drug discovery process. Although there's a limited demo here in the class.